Tranquila.
Sorry, before we start, I would like to make an announcement. We have with us Silvia Ortiz. She's a postdoc that will come for a year. She comes from the ICA, Instituto de Cantabria. She has worked there for a number of years, so 10 years postdoc and PhD. And she will work in the collaboration project in Mexico. And we also have 6 new software students who are
Well, I have the pleasure to introduce Ricardo. Ricardo studied physics in the University of La Laguna in the Canary Islands. Then he moved to the Balearic Islands to do his master and his PhD also. That he was finished last year. And then he moved to Princeton University to the group of Simon Levin in the Department of Ecology and Evolutionary Biology. Working mainly with Corina Tarnita about the evolution of multicellularity. I think he's going to talk.
Yeah.
Today.
Thank you, Cristóbal. Thank you for being here. It's Friday afternoon, so it's not the best time for being a seminar, so thank you very much.
Oh, sorry, Ricardo will be the whole month of July here. So if anyone...
Well, if you don't like me, I will be as well.
talking to him, so...
So yeah, thank you very much. Thank you very much for being here. The things I'm going to tell you today are mainly the things we have been working since I'm there, so last year basically. Part of the results have been also, the project started before I went there, so it's part of things, both of these things. So just to start, when we want to study how the multicellularity evolves in nature, there are mainly 2 ways of reaching that multicellularity. So one of these operations can be called staying together, and it's basically the one that all of us have performed. So basically in this operation, we start from a single cell, and then this cell divides, and for some reason it stays together, and then start dividing, and at the end, some complex is formed. So this is the way that mammals and plants and many reach multicellularity, and in somehow it's interesting as well, but it shows not that, all the cells here have the same genotype, so they are clonal, and if we want, if some kind of conflict appears here, it might be because of some mutation that then is a bad mutation of things like cancer and this kind of illness. So the other operation that we can define is what we call coming together, and this is in principle is particularly interesting because we can have different cells with different genotypes that for some reason can form a group and can evolve a multicellular complex. So this is, as I have said, this is particularly interesting because it shows a huge phenomenology of conflicts. Like we have, in principle, different types of cells that are not very related genetically, and they can have conflicts, and they can. Selection is going to be more intense here. And in this scenario, one of the organisms that uses this mechanism to reach multicellularity is the cellular slime molds, which is the organism that we are working with, and whose life cycle I'm showing here in this picture. So basically, these guys, what they do is they feed on bacteria. They live as single cells, eating bacteria and dividing by cellular division. And at some point, when they consume all the resources in the environment where they are living, they do this coming together. So they aggregate, and they form in principle, they form a mound of cells that then starts a developmental program and forms a fruiting body where we have 2 kinds of cells. So in this fruiting body here, we have spores that are going to be reproductive cells, and we have the stalk here that is going to be cells that actually die, and they are going to die, and their only work here is to rise these spores from the ground and to give some kind of, to give these spores the opportunity of being dispersed to a different environment.
Do they have different DNA?
So as in principle they can. You can have different genotypes that are living in the same environment, and they can aggregate together. And then that's why different conflicts may appear, because when you have a lot of cells that come from the same parent, then you can apply like kin selection and things of rules that say, okay, they are genetically related, so in principle this kind of altruism makes sense. But if they don't have that relatedness, then it's more interesting what is happening here. So, what we observe in these organisms when we go to the field and we catch them is that about 10% of the fruiting bodies that we are taking from the ground are chimeras. This means that they are formed by at least 2 genotypes. So, as Ingo asked, we can have a lot of clonal fruiting bodies, so all of them have the same genotypes, but 10% of them have different genotypes. And of course, as I said before, there is some pressure in these fruiting bodies to be in the spores, because the cells that are not going to be in the spores are going to die. And so actually what happens is when we have a mixed population with 2 genotypes that we can call here blue and green, and we allow them to aggregate, so we remove all the food and they have to do the fruiting body. If we count the spores in this fruiting body, we observe some skewness in the fraction of the spores. So we have, for instance, 60% of blue spores and 40% of green spores. So the thing about this is that we have always these hierarchies in the fruiting body. So always, every time that we mix blue and green cells, blue is winning. And chimeras, although they are not frequent, if we have always this genotype winning over the other one, in principle, if we allow this to happen for a very long time, blue cells are going to win, right? Because every time they are more abundant than the green ones, and at some point they are going to kill all the green ones. But the thing is that when you go to the field and you look at the genotypes of these cells, there is a huge diversity of genotypes in the field. So this very big diversity is completely opposite to this skewness in the reproductive fruiting bodies. So in principle, to explain this, what one can think is that the spatial structure of the population is going to play some role, and then we can have. These are the results from an individual-based simulation that we are working on, and you can have, in principle, originally the red genotype was growing. You will have all the genotypes, all the fruiting bodies being clonal with red cells, where the black genotype was growing. You will have all the black cells. But then in the frontiers of these regions, you will have these chimeras. The thing is that, of course, this can explain the formation of chimeras, but this doesn't explain the linear hierarchies in the genotypes. Because here, of course, if you have some mixed population in the frontiers of the regions, you will have sometimes, as you can see here, the black genotype winning and sometimes the red one winning. So in order to be able to explain these hierarchies, we need some. Well, linear hierarchy, it means that what it means is that every time that you mix 2 genotypes, you will always have one genotype winning over the other one. And if you mix always the same, and if you mix the winner one with a different one, maybe that is winning, and you have kind of
potential dominance of one of them.
Yeah, one is like the dominant, and at the end that will kill the diversity in the system. Yeah.
Why linear?
Sorry.
Why linear?
I guess it's because it could be monotonically increasing, but I mean, you don't have this kind of this winning this, and you have like a progression in the winners. So I think they call that because of that. I don't know. Yeah, that's a good question. So yeah, to be able to explain this thing, what we propose is that actually the fitness of these guys has 2 components. So when you observe this aggregation happening, not all the cells in the plate are being part of the fruiting body, right? And this is something that people have observed from many, many time ago, but they didn't look at them. I mean, they just thought that they were mistakes in the for some reason they were not responding to the signal, and then they were dying because of not being able to aggregate. So yes, I want you to see this video. It's an experiment. So these are single cells, and at some point they have already consumed the resources, and now at some point you will observe how they start aggregating.
Time and space scales.
Yeah. So sorry. The time scale. The video starts 5 hours after they consume all the resources, and this video is going to be until 18 hours after aggregation. So the whole cycle takes in between 15 and 24 hours. And the space scale, this is a petri dish. Well, the middle of it, more or less. So yeah, I mean, I didn't do this video. That's why I don't know. Yeah, I'm not going into the lab. So here at some point you will observe how actually here aggregation has already started and all the cells are going together. And as you can also see, we have here some guys that are completely behind the aggregation, and they are not going to be part of the fruiting body that at some point is going to be formed. But they are moving, as you can see here. They are still moving. Now the mound is formed, and they are forming like a slag that is going to do some thermotaxis and is going to move to the light and is going to look for a good place to reproduce, basically, to send the spores. Yeah. Now this is supposedly to be growing up, but the video is not very good for this. It's good for looking at these loner cells. That, as you can see, they might. I mean, there is a reasonable fraction of them. So. So yeah, with this email, what actually the experimentalists we are working with did was to plate some of these cells with some bacteria that you can observe them here, and at some point when they consume all the bacteria, they are going to aggregate and they form these fruiting bodies here, and then this is each figure is after 1 day, so this is day 0, day 1, day 2, day 3. So when they do these fruiting bodies, what the experimentalists did was to remove the spores from the plate, and then they put more bacteria into the plate to allow the cells that were not aggregating to reproduce again. And as you can see here, they were able to reproduce and to form new fruiting bodies. So in principle, this is something that is telling us that these cells that don't aggregate actually are completely viable. They are going to be able to keep on reproducing, forming aggregates, and doing whatever. I mean, the only thing is that they don't aggregate at some point. So this experiment was done by people in the university we are working with, but also some group in France that is actually experimentalist, and they have been working in this for many, many years, has got the same results as we did. So the thing now, the question that we should try to figure out is why these cells are not aggregating. And the thing is that when as I said in the beginning, when these slime modes aggregate, they have to follow a developmental program that takes quite a lot. I mean, once they start aggregating, they are completely committed to go on with the whole process. In this sense, every time that they are going to start aggregating, they are going to have to spend 24 hours forming this slag, fruiting body, and all these things. Additionally, once the fruiting body is formed and the environment becomes good again, these spores need about 4 hours to be able to germinate and to give rise to new cells and all these things. So in principle, aggregating it's timely costly. I mean, you have to invest time on doing this. So if you are in an environment where the food is going to come back fast enough, then it's to aggregate, because you are going to be able to survive that short time without eating, and then food is going to come and you are going to outcompete all the guys that did aggregate. To do that, so with this in mind, what we propose is that loners and spores constitute a bed hedging strategy, and a bed hedging strategy means that when you have to reproduce in some place that is very stochastic and you don't know very well what is going to happen, then it makes sense, instead of saying, okay, I will put all my, let's say, money if you want, or fitness in this case, on this side, or I will put all my investment in this side, I will split it. So I will put something here, so if the environment is more or less fluctuating, I will be able to survive. So that's what we propose, that spores and loners are a bed hedging strategy, where spores are a survival strategy. So the spores are going to be more resistant to starvation, they are going to be able to live longer without food. And this is also an exploration strategy, because as I said in the beginning, the fruiting body is going to rise up, and some insects that are going through the ground or wherever are going to catch some spores, and they are going to be dispersed easily. And these loners are the exploitation strategy because they are going to be able to adapt faster to environmental changes, and also, yeah, they are going to start reproducing. They are going to start reproducing faster than the spores. So, hedging strategy. I mean, thinking of this hedging strategy, what we propose is a mathematical model without space. So, yeah.
Is this the strategy done at the level of individual or at the level of population? So every individual is this, or some individuals in the population always do one thing and some others?
No. So what we think is that phenotype, the population is going to split always in the same fraction, like let's say 90% of spores and 10% of loners. But if you at some point in some starvation period you are a loner, then you are going to be able to completely make a spore. So you are not marked to be a spore or a loner, but with some you have a given probability to be a loner or a spore, and that probability depends on the genotype you are. But that's something we think. We don't have by now experiments to confirm that. So yeah, the model that we propose is population level model. So we're going to write differential equations for each thing that I'm going to show you later. But the model is basically, if this is time, we start with some starvation period, where we don't have food. So in that period, we have all the cells die, right? At some point, after some time, the food comes back to the system, and then cells are going to, first of all, the cells are going to start growing, and after a time tau, that typically is going to be those 4 hours that I told in the beginning, the spores are going to germinate, and both the spores and loners are going to start reproducing back again. After some time, when they eat all the resources, then starvation period is going to start again, and they are going to die for some time until a food pulse is coming back to the system, and then loners grow, and then spores germinate, and they grow again. So the thing here is that we are using, I'm showing you here the case where starvation times are stochastic. So we are drawing them from some exponential distribution. Other groups are trying different distributions, and I will also show you the case where we have this time completely fixed, just to compare what's happening in each case. So if we write this into equations, then, what we have basically is that we start in the starvation, then when the growth period starts, the spores are growing and dying. They grow with some Michaelis-Menten dynamics, which is basically telling us that they are eating the resources. As you can see, resources are also consumed with the same term. And before spore germination, and the spores don't do anything because they are dormant, right? They remain constant. After some point, when we have the spore germination, we have a fraction of spores that becomes cells, and the spores go to zero.
Sorry, what is the
Alpha is the genotype. So we are going to have many genotypes, and actually alpha is going to tell us what you asked before. It's going to tell us the fraction of cells that are going to be loners and spores after each aggregation process.
Is the growth rate somehow derived from the spatial properties of the system, or is it just an ad hoc assumption?
The growth rate, this growth rate C, is the doubling time that we measure in the lab. So this, when you put a population of N cells in a petri dish, they take 4 hours to double the population, and we fix this C to have that.
The way the food is consumed,
yeah,
will depend on the spatial degree of freedom.
Depending on the initial conditions that you have, yes. But if you start with a well-mixed population with high enough density, you can remove that effect. Actually, in the individual-based simulation that I showed you the pie charts in the beginning, we are taking into account that spatial thing. Yeah. So then, after all the resources are consumed, we have this population splitting in between spores and loners. And this alpha, as I told before, is so a fraction alpha is going to be spores, and the remaining 1 minus alpha is going to be the loner cells. And then they are going to die exponentially in the starvation period, assuming that loners die faster than spores. So mu has to be much bigger than delta. and resources are going to be 0. After some time, food recovers, and we have a new food pulse.
How many parameters do you have?
Parameters, we have only alpha.
Delta, mu.
Delta is measured experimentally. Mu is measured experimentally, but we have it 10 times bigger than the spores one, and we do some sensitivity analysis to this, and it's not. I mean, it's only going to split somehow the results. And then R is the amount of food that you want to put. So when you do the experiment, you can do that, and this is fixed also with the doubling times. And sorry, C is the doubling time of the population, so it's the rate at which they grow. And S is also the fraction of spores that become cells, and it's also measured experimentally. And I think that's all. Yeah.
Why is alpha not?
Alpha is the fraction of. Actually, now we are going to start doing experiments to know that. Alpha is the fraction of cells that become spores in each genotype. So now we have to do the experiments to say, okay, we are going to put this genotype, let's count them. But by now we don't. I mean, we don't know. We know that they do. I mean, they split in different ways, but we don't know if the range is between. We don't know actually. So to do the simulations, what we are going to take is 21 genotypes that are going to go from alpha equal to 0 to alpha equal to 1. So we are going to have from a genotype that makes a lot of spores to a genotype that doesn't make spores. And we are going to use 25 environments. And the environment, well, I will show you it now. So here what I'm showing you is which is the genotype that wins. So when you integrate these equations, numerically, at some point you have all the populations going to 0 and one population that is going to a stationary state. So what I'm showing you here is the frequency of each genotype in the steady state. So which is the winning genotype. Here we have the genotypes, the 21 genotypes that I told you, and here we have the 25 environments. We are defining the environment by the mean starvation time. So by the time that the starvation period, by the length of the starvation time on average. So when we have an stochastic environment, this lambda is the mean value of that exponential distribution, and when we have a fixed starvation time, lambda is the starvation time. And yeah, what you observe here is that when we are in very fast environments, then what makes sense is not to make spores. And when we are above some starvation time, what makes sense is to make spores. Here we have that making only loners or making only spores is the better strategy. And this is any kind of stochasticity in the environment. Actually, what happens, well, we got these results, and also the group in France that I told you got the same things. So what happens when we go to an stochastic environment is that as now we have to overcome some uncertainty in the environment, what makes sense is to do this bed hedging strategy that I mentioned before.
What is stochastic?
Stochastic in the sense that when we have when we finish with the growing period, so when the resources go to 0, then we have to draw the length of the starvation period, and we take it from an exponential distribution. So sometimes we have lambda, in that case, would be the mean value of the distribution, and you have some variation here.
So the length of the starvation period, but not the food?
No, the food is fixed. The amount of food is fixed. The only thing that changes is the duration of the starvation period. So sometimes it might be, I don't know, some hours and more or less. So that's, in that case, makes sense to split your beds to be able to survive both to the cases where food is going to recover fast and to the cases where food is going to recover slowly. Actually, here you see that we have we have maybe 2 genotypes being in the system, and this is because we are discretizing the genotypes. So we are taking a grid that is with some resolution. For instance, if we here have 0.55 and 0.6, if the winning genotype is 0.57, in some realizations we're going to have 0.5, sometimes 0.6, and that's why you have frequency. But in the paper we show analytically that only one strategy is going to be able to win when we have only one environment. Right, so yeah. So what happens is that when you are in very, very fast environments, of course, making loners makes sense. In the other extreme, when you have very, very slow environments, spores is going to be better. And in this width here, what makes sense is to split your survival strategy. And with this result, we propose, in order to explain this chimeric skew in the fruiting bodies, what we propose is that actually, if you pick types that have different ecological histories, so they come from environments with different ecological conditions, then they are going to have different investment in spores and loners, right? So if you go to some place where food is usually coming back very, very fast, if you pick that genotype, it is going to make mainly loners, and if you pick it from an environment that is very slow, it's going to make mainly spores. So with this, what we say is that if you mix them and you make them compete and make fruiting bodies, this chimeric skew that you observe in the lab is going to appear, but it's going to appear before the aggregation. And it's going to appear because some cells are going, one genotype is going to invest more in the aggregation, and the other genotype is going to invest less in the aggregation. And then what we propose is that these genotypes don't interact at all, so they are completely, and that skew is appearing because people in the lab only count the spores. So if you only count the spores and you have that prior skew that tells that some cells are going to be, some genotypes are going to invest more in spores and some genotypes less, then you have that skew. So just to put this with pictures that I think is easy to understand, at least for me, if you remember the picture that I showed you in the beginning, we had this thing, right? We have 100 blue cells and 100 green cells, and when you mix them, you may have 72, 48, 60, and 40%. So what happens then if we take only the blue spores and allow them to aggregate? So with this splitting in between spores and loners that we have been talking about before, we may have like 10 cells being not part of the fruiting body and 90 cells being part of the fruiting body. And inside that fruiting body, we have 72 being spores and 18 being stock. So actually here, when a fruiting body is formed, the 80% of the cells are going to be spores and 20% are going to be always in the stock. That's the relationship in between cells in one side, and that's why this 72 and 18. And then if we take the blue population, we take 100 cells, let's say, and then these cells this green genotype comes from an environment that is faster, so they are going to make less spores and more loners, and we have, let's say, 40 loners. Then we will have 60 cells in the fruiting body, so we have a smaller fruiting body. And following that relationship that says that 80% are spores and 20% are stock, we have 48 spores and 12 stock cells. So then, if we now mix green and blue cells and they don't interact at all, let's say what happens. Let's see what happens. So what happens is that if they don't interact, we will have 10 blue loners and we will have 40 green loners. And if we go into the fruiting body, we will have 52 blue spores, 48 green spores, and 18 blue cells in the stock and 12 in the stock. We have this this skewness in the fruiting body. So the blue genotype is going to be always overrepresented in the fruiting body, but not because they are winning over the green one or because of whatever. It's only because they are having more cells in the fruiting body, and then of course they are going to be more abundant in the spores if they are already more abundant in the fruiting body. So what we say, we're not saying that there are not social interactions between these cells. What we are saying is that it is impossible to draw any kind of conclusion about the existence of this relationship if you don't go to the lab and count all the cells. Because the fitness is not one-dimensional. You have two components in the fitness, and you, of course, have to count all of them. So we got this result, and also the group in France got the same thing. And what I'm going to show you, that is already the last part, is things that, it's something that we did. So because by now we have explained that this chimeric skew is appear, but it does, I mean, in principle it might be not because of the social interactions.
Sorry, but the suspension, the situation you explained here has been repeated the next day, or is just a hypothesis? When you mix those, you get that?
What we want to, I mean, the thing is that they have checked this in, I mean, it's hard to check this in wild genotypes because it's hard to be able to distinguish in between one genotype and the other one because you cannot mark the different genotypes. So, yeah, actually by now the experiment that one should do is the one that Ingo asked before about, and is being able to characterize each genotype with the fraction of spores and loners that it does. And I think this would be like the second step. I think. But, yeah, we have explained this chimeric skewness, but we haven't been able to explain the huge diversity happening in nature, right? So to explain that, what we propose is that dispersal in between different environments is going to give you that diversity. So what we did was to pick the 25 environments, that I showed you before, and allow some dispersal in between them to happen. The way that we did was to think that we have from very fast environments to very slow environments, and when the spores are formed in a given patch, then a fraction of them is going to be dispersed over the other environments. So what we get integrating this in the 25 environments is that, well, this panel is the same as before, just to compare. So here we don't have any kind of connections. Here we have 1% of the spores made in one environment being dispersed to the other ones. So for instance, when spores are formed in this environment, in 1040, 100% of the spores are dispersed over the other 24, right? It's not 100 in each one, 100 over over all of them. And what we observe here is that still the main diagonal is winning. I mean, it's the most abundant one, but we have some cloud of genotypes being able to live, to coexist. If we increase the fraction of spores dispersed to be the 10%, we have already like two clouds being formed, right? We have here this green one and this other one here, and we have even more genotypes being able to coexist. If we keep on increasing the dispersal fraction, we observe this cloud to be going towards the smaller alpha, and at some point, if we go to very, very fast, to very high dispersal, what we observe is that these two clouds merge at some point, and we have a bed hedging strategy being the winning one over the whole environment. Well, we have some cloud here, but the reason why this is happening is because at some point, if you have a very big dispersal and also you have these environments, in principle, are completely, I mean, they are not synchronized. So when aggregation is happening in some of them, food is happening in other ones. So at some point, if you connect them with a very, very high dispersal, you are kind of living in a global environment where you have all the patches connected and you have a bed hedging strategy winning in the whole scenario. Well, apart from these guys here that are so fast that nothing is going to survive there apart from loners. Yeah, just to finish, two main conclusions. The first one is that, as I already told, chimeric interactions are not necessary to explain the reproductive skew in the fruiting bodies of the Diosteum discoideum, which is the name of this cerebral slime mold. And the second one is that even under I think the most simple assumption, that is the neutrality hypothesis that says that these genotypes don't interact at all, it is possible to show the great diversity of genotypes as a consequence only of the ecological conditions that they are where they are living. And yes, also 3 points that could have like higher implications, because probably at this point you are wondering, well, which kind of relationship has all these things with the evolution of multicellularity and all these things, right? So the idea is that having these bed hedging strategies and having the loners as a component of the fitness of these guys, you can have somehow you have a reservoir of social behavior that is going to be able to stabilize the formation of fruiting bodies. So if you don't have that reservoir, maybe you have cheaters being more able to infect that social behavior and being able to completely destroy the cooperation. So if you have these loners, of course, loners are hard to cheat than the sports, right? Because what is happening here is that what a cheater makes is basically when you have these guys going together, the cheater is going to be so smart that he's going to tell every time, okay, I don't want to be in the stock because I don't want to die. So now you are going to die, I'm going to be in the sports, and you do all the stuff for me. What happens when you repeat these things over and over? Once a lot of times in time. What happens is that at some point you will have only cheaters because the cooperators are going to be in the stock every time and the cheaters are not going to be, and the cheaters don't know how to do the stock. So at some point the whole population is going to die. The thing is that if you have that reservoir of loners, these loners are not going to be cheated any time because they don't have the way to be pushed into the stock, and they are going to be able to maintain this social behavior. The second thing is that, the second thing is also based on this and says that having this bed hedging strategy and also taking into account the ecological history of these guys is important to think of the evolution of multicellularity, because depending on we have seen ecological conditions, you might have different investment in the spores and loners and these things. So ecology is important. And the third thing is work we are doing now and is related with additional trade-offs that appear in these slide modes. So here we have only looked at the trade-off in between living in fast environments and living in slow environments and doing spores or not. But they have many, many other trade-offs. So we have genotypes that reproduce very fast. So they have a lot of children, so to speak. But these cells are very, very small. So they are going to be weaker. Then we have cells that, because of they reproduce so fast, they are going to be more abundant. So they are going to be overrepresented in the fruiting bodies. And we have many, many, many trade-offs. And that's something that that is going to be, the ecological history of these these guys is going to mark all these trade-offs and is going to be important as well in order to study how the social behavior is going to success or not. And yeah, that's all. Thank you. And this is the paper that we published already. And this is the people working on this. She's Corina. She's my postdoc supervisor. I'm actually working in his group, not in Simon's Levin one. And Alex is, he was a PhD student of Simon Levin. He was doing all the theoretical work before I came. Then we did it together. Alison she's a postdoc there in the physics department. She's doing all the experiments. And Simon Levin, sorry Simon. He's a professor also in the department and doing also theoretical things. And yeah, so if you have any questions. Yeah.
I have a question, maybe I misunderstood. In the beginning you said that in nature about only 10% of these slide moles are chimeras. Is that correct?
Yeah.
So in that sense, if one would do experiments, one would easily have, if I does some statistics, see whether actually the different genotypes play a role or not, and whether the bad hedging strategy is actually implemented or not. Do I understand that wrong?
Well, if you...
Because most of the experimental realizations that you would do would be having only a single genotype.
Well, I think that, and that's something I think, because I have been in the lab twice, that if you mix the population, then you are able to increase the fraction of chimeras. So it's more or less, you have more...
But it would be easy to see what happens for a system which only has a single genotype.
What do you mean? If you have only one genotype, you don't have chimeras.
You don't have chimeras, but you see whether this bad hedging strategies...
Yeah, sure. But then it's, the thing is that it is hard to... So if we go back to the video, it is very hard to count the cells that don't aggregate. And it's also hard because, well, there are many like technical things that honestly I don't know. But it's very hard because at some point you have, so for instance, when you have this guy moving, all these cells are not loners, for instance. They are just left behind of of this guy because it's like moving and then. So I think it's the hard thing of counting these guys is more a technical issue than. But yeah, honestly, when I started thinking of this, I thought it was going to be like a very, very easy experiment. But then when you talk with experimentalists, you should know. Well, you know, this is not that easy. But I was very excited because it was okay. I have this, and then I can count. These cells are not so small. But I think it's hard to count the cells that don't aggregate. But yeah, it's doable. Yeah, it's feasible.
In all the plots in which you draw the selected genotype with respect to the speed of the environment, there is always a speed of the below which only the donors win.
Yeah.
What is this time scale? Here.
Well, here or here.
At 7 or here at 400, there is a transition. What is this time scale?
This is ours. So when you have an environment that recovers with this on average, then it makes sense.
But what determines this number?
So it is determined by of course, by this parameter, so by the growth and death rates, and mainly by this, also by this fraction of spores that is going to be able to survive. Basically, what is going to tell you where that transition is the cost that the spores have to pay because of aggregating. So if you have a very high cost for aggregating, that making loners makes sense farther. But if the cost is very, very slow, then it makes sense. It depends on because with the parameters, how you tune or well, how you fix the cost of aggregating versus non-aggregating.
Can you calculate this transition time?
So in the deterministic environment, we calculated this analytically. Yeah, and it depends on those parameters. Yeah. I didn't do that, Corina did.
Can you explain a bit which kind of interactions we're talking about?
Yeah, so it might be, for instance, the thing is that when they eat all the bacteria, they start communicating to say, hey, I don't have food, let's go together, right? More or less. So what happens is that there are some, no, that's what happens, like the gazelles. So what happens is that there are some cells that are less resistant to starvation, so they start signaling before, and they pass that signal through the whole population, and then they start communicating and going together. What happens is that once they form the mound, for instance, they keep on communicating to have that differentiation of labor. Sometimes the guys that are going to be in the spores are the guys that were early in the life cycle, so that are going to be more resistant to survive. And what happens with the jitters is that, for instance, they have somehow they don't respond to that signal, so they are going always to go to the spores. They don't want to be in the stock because they would die, or I don't know, or cells that are able to that are able to make the stock, but if somehow they feel if they are with other guys, so if there are other guys, they don't do the stock, but if they are alone, they do, or there are many ways of, basically it's taking advantage of these altrins and avoiding as much as possible being part of the stock. And always with this communication. They have that communication modified.
Are you planning to make special models?
Yeah, we are doing actually the special model, but yeah, I didn't show you that.
The motion of the particle?
Yeah, we have it.
Brownian?
So they have two phases in the motion. When they are feeding, they are mainly Brownian, but not at all. I mean, not completely, because they feed on bacteria with chemotaxis. So bacteria are secreting some folic acid, and these amoebae are able to follow that signal and to eat. But they are mainly Brownian. And then when they start communicating and they start following that aggregation signal, then they are completely, they are very, very directed to the target. And what we are doing in the model is having those two phases. At some point we have Brownian or more random, and then we have less. Yeah.
This one. So at the bottom, the lower two figures, you see that at 0.5 you start with a certain probability which then disappears.
This one.
Yes. So here you have at 0.5 right at the beginning, at a very short salvation time you have blue or turquoise, and then it drops to blue again.
Well, the thing is that first of all, if you see the scale of this dark blue and light blue, it's very tiny. And here, this is but it's not as dark.
Yeah, but
so,
it's repeated in the figure to the left as well, so it seems to be systematic.
Yeah, but the thing is that because of the resolution here in this color bar, this might be probably part of noise or yeah. But those simulations were like huge because you have these 25 environments with 21 genotypes. So at the end you have 21 times 25 that are asynchronous. So yeah, I tried to do longer, but this simulation was like 2 months of computation. So I think Vera would not be very happy if I took 4 months. Because you didn't know. I thought you used 2 months. Yeah. Forms a fruiting body where we have 2 kinds of cells. So in this fruiting body here, we have spores that are going to be reproductive cells, and we have the stalk here that is going to be cells that actually die, and they are going to die, and their only work here is to rise these spores from the ground and to give some kind of, to give these spores the opportunity of being dispersed to a different environment.
Do they have different DNA?
Yeah, so in principle they can. You can have different genotypes that are living in the same environment, and they can aggregate together. And then that's why different conflicts may appear, because when you have a lot of cells that come from the same parent, then you can apply like kin selection and things of rules that say, okay, they are genetically related, so in principle this kind of altruism makes sense. But if they don't have that relatedness, then it's more interesting what is happening here. So one of these operations can be called staying together, and it's basically the one that all of us have performed. So basically in this operation, we start from a single cell, and then this cell divides, and for some reason it stays together, and then start dividing, and at the end some complex is formed. So this is the way that mammals and plants and many reach multicellularity. And in somehow it's interesting as well, but it shows not that all the cells here have the same genotype, so they are clonal. And if we want, if some kind of conflict appears here, it might be because of some mutation that then is a bad mutation of things like cancer and this kind of illness. So the other operation that we can define is what we call coming together, and this is in principle. It's particularly interesting because we can have different cells with different genotypes that for some reason can form a group and can evolve a multicellular complex. So this is, as I have said, this is particularly interesting because it shows a huge phenomenology of conflicts. Like we have, in principle, different types of cells that are not very related genetically, and they can have conflicts, and selection is going to be more intense here. And in this scenario, one of the organisms that uses this mechanism to reach multicellularity is our cellular slime molds, which is the organism that we are working with, and whose life cycle I'm showing here in this picture. So basically, these guys, what they do is they feed on bacteria. They live as single cells, eating bacteria and dividing by cellular division. And at some point, when they consume all the resources in the environment where they are living, they do this coming together. So they aggregate, and they form in principle, they form a mound of cells that then starts a developmental program and form a kill.
Sorry, before we start, I would like to make an announcement. We have with us Silvia Ortiz. She's a postdoc that will come for a year. She comes from the ICA, Instituto de Cantabria. She has worked there for number of years, so 10 years postdoc and PhD. And she will work in the collaboration project in Singapore. And we also have 6 new software students who are welcome.
Well, I have the pleasure to introduce Ricardo. Ricardo studied physics in the University of La Laguna in the Canary Islands. Then he moved to the Balearic Islands to do his master and his PhD also. That he was finished last year. And then he moved to Princeton University to the group of Simon Levin in the Department of Ecology and Evolutionary Biology, working mainly with Corina Tarnita about the evolution of multicellularity. I think he's going to talk.
Yeah.
Today.
Thank you, Cristóbal. So yeah, thank you for being here. It's Friday afternoon, so it's not the best time for being a seminar, so thank you very much.
Oh, sorry, Ricardo will be the whole month of July here. So if anyone
Well, if you don't like me, I will be as well.
talking to him, so
So yeah, thank you very much. Thank you very much for being here. So yeah, the things I'm going to tell you today are mainly the things we have been working since I'm there, so last year basically. And part of the results have been also, I mean, the project started before I went there, so it's part of things, both of these things. So just to start, when we want to study how the multicellularity evolves in nature, there are mainly 2 ways of reaching that multicellularity.